Video is not working. So, Professor Mitra, we will start. Maybe others will be joining. Okay. You are mute. Are you mute? No. You are mute possibly.
Sir, namaste, sir.
Namaste, namaste.
Sir.
Professor Mitra, can you hear me?
Yes, sir. Yes, sir.
Oh, yes. Now you are
Sir.
also audible. Okay.
Yes, sir.
Namaste. So we'll start. Very hearty welcome to the 66th Distinguished Lecture Series being organized by INAE Bhubaneswar chapter, IIT Bhubaneswar, IMMT Bhubaneswar, Niger Bhubaneswar, SOA University, and IOC ICT Bhubaneswar campus jointly. I am really very happy to say that today's lecture is by Professor Rahul Mitra, who was also my colleague. During my period also, he was my colleague. And he is going to talk on design and development of materials for ultra-high temperature aerospace application. a very, very niche area. So where he has done extensive work. I'm not really going to read the abstract, which you will possibly, you might have already read it. And during his talk, actually, he will also explain what it is. So far as Professor Mitra is concerned, Professor Rahul Mitra received his BTech honors in metallurgical engineering from IIT Kharagpur in 1988 and PhD in material science and engineering from Northwestern University, Evanston, Illinois, USA in 1992. Thereafter, he joined DMRL Hyderabad as scientist in 2002 and moved to IIT Kharagpur, where he is a professor in metallurgy, metallurgical and materials engineering, and served as the head during April 2017 to 2020. He also served as the head of School of Nanoscience and Technology during October 2016 and December 2020, and chairman of Central Research Facility during December 2009 to 2017. He was on sabbatical at Northwestern University, Evanston, Illinois, and University of Southern California. His research is focused on silicide-based intermetallic alloys, ultra-high temperature ceramic matrix composite, as well as carbon fiber reinforced composites with emphasis on microstructure, deformation, oxidation behavior for nearly 3 decades. He has also worked on processing and mechanical behavior of lightweight metal matrix composite as well as nanocrystalline thin films. He has worked as principal investigator on several sponsored projects with the total value exceeding 16 crores. He has authored or co-authored 219 publications in peer-indexed reviewed journals, 11 book chapters, 2 patents. H index is 45 and I-10 index is 157, as well as guided 30 PhDs to completion. Furthermore, he has authored a book, Structural Intermetallics and Intermetallic Matrix Composite, published in 2015 by CRC Press. He has also edited a book with the title Intermetallic Matrix Composites, Properties and Application. He is the recipient of large number of awards, which includes MRSI Medal in 2003, the Metallurgist of the Year Award in 2014, GD Mirla Gold Medal in 2021. He has been elected Fellow of Indian National Academy of Engineering in 2016, Electron Microscope Society of India in 2017, Indian Institute of Metals in 2022, National Academy of Sciences India, NASI in 2023, Indian National Science Academy, INSA in 2025. He is member of the editorial board of Sadhana, published jointly by Springer and Indian Academy of Sciences, and as well as editorial advisory board of transactions of the Indian Ceramic Society, published by Taylor and Francis. He has served as expert member or presently as a member in several national committees under DST, FAST, WS scheme, SERB, DRDO. Presently, he is the subject expert member of the Engineering Science Research Committee for CSIR extramural research schemes in the area of engineering sciences, Technical Program Committee for the Materials Mining and Mineral Engineering of the Advanced Research Grants under Anusandhan National Research Foundation, New Delhi, as well as the DRDO Industry Academia Center of Excellence, IISc Bangalore, IIT Kanpur, IIT BHU, and the list is quite long. So now actually I do not know if any of our other institutes, anybody actually from those institutes are present. Of course, I know actually Professor Renu Sharma, who represents actually the IEEE Bhubaneswar chapter, who is also one of the, our partners in this all these activities. She is present. Now, with this actually brief introduction of Professor Rahul Mitra, may I now request you, Professor Mitra, to please make your presentation. You are mute. Kindly unmute. No, it's not audible. Namaste. No, still there is some problem.
Or shall I leave again? Maybe that's
Yes,
better.
yes. Now absolutely is fine. Please go ahead.
Now I cannot hear you.
Oh, you cannot hear me. Okay. Anyway, please go ahead. I think we can hear you. All right.
But earlier I was audible. I don't know what happened. Is it okay?
It is okay. We are able to listen to you. Please go ahead. I think things will be all right.
Am I audible? No?
Yes, sure. Perfectly.
Now I cannot hear.
Okay. Can you hear us?
Okay.
Okay, please go ahead.
Am I audible now?
Yes.
Yes, sir.
Something is. Am I audible now?
Yeah. Please.
Yes,
Okay.
sir, you're audible. You're audible very much.
All right.
Please.
So, good evening, everybody. It's an honor for me
Very
to
good
be here
evening.
in front of
Please.
this August audience of INAE Bhubaneswar chapter. I thank Professor Damodar Acharya, our former director, very profusely for inviting me and having me here. So, as you mentioned, I'll be talking about my research on development of materials for ultra-high temperature aerospace applications. So, it was mentioned that I was in DMRL earlier. So, I got involved in this area since my stay in DMRL. So when we talk of materials for high temperature applications, we basically are interested in developing materials for very high operating temperatures to avoid the requirement of extra energy that is required for cooling during application. So you know that in a gas turbines, the blades are actually cooled by air cooled. So for that extra energy is required. Now that can be avoided if the materials are developed for operation at high temperature. So now what is important is performance, reliability, and life of components. The components could be components in jet engines, it could be rocket nozzles, then sharp leading edges of re-entry vehicles, and missile launchers and arc plasma electrodes. So this, when we say ultra high temperature, we mean temperatures above 1000 degrees centigrade, or even higher. So the major requirement when we talk of high temperature materials is high melting temperature. So because you know that close to melting temperature, materials become soft. So that's why we need to operate, we need materials which are very high melting temperatures. And they should, as I mentioned to you, that it becomes soft very close to the melting point. So materials should be able to retain strength at high temperatures. Another property which is important is high creep resistance. That means creep is a property at high temperature, which is basically time-dependent deformation. So if the material can retain its strength at high temperature, its creep resistance is also increased, and it should be able to resist damage by thermal shock and gradient, because often these materials are exposed to thermal gradients. One side is at high temperature, the other end is at lower temperature, or there is repeated heating and cooling. Then it should not fail under such conditions. Then it should resist environmental degradation by oxidation and ablation. So this is another property which is very important for materials which are exposed to re-entry from outer space. So they are exposed to at very high temperature, they're exposed and they are bombarded with particles. So they should be able to survive under such conditions. So those are basically very extreme conditions. Now, if we see the plot of specific tensile strength versus strength retention at high temperature, you can see that we start the graph from carbon fiber reinforced composites, then titanium matrix, metal matrix composites, and so basically all these are at low temperature. But these fibers, these are basically plastics. This is CFRP is carbon fiber reinforced plastics, then steels. So metals and alloys, they go up to about 700, 800 degrees centigrade. After that, problem is of oxidation. Nickel-based superalloy can actually go a little higher, up to 1100 degrees centigrade, you can see. But the strength comes down significantly. So in this temperature regime, the ceramic metals composites and refractory metal composites or refractory metal alloys, they are the options where we trying to operate. So you see that we have carbon silicon carbide composites, carbon silicon carbide, silicon carbide, carbon composites. So these are the materials which are used in re-entry vehicles like missiles, and also in certain parts of aero engines where temperatures are above 1200 degrees centigrade. And then the silicides, refractory metal silicides. So these are also like molybdenum silicides, niobium silicides. They can operate at temperatures up to 1300 degrees centigrade. Then the property of thermal shock is plotted as thermal diffusivity. You see that thermal shock increases as thermal shock resistance increases as thermal diffusivity increases. So there is a correlation. And this is very important for metals, refractory metals and ceramics, particularly ceramics which are brittle in nature. because when you do heating and cooling cycles, the thermal stresses which leads to fracture. So another property which is important is to form a stable and protective oxide scale, which will protect from further oxidation. So in this case, what is important is the thermodynamic stability of the oxide scale that is forms, and the growth rate should be optimum as the depth of oxidation is minimum, and the oxide scale should be continuous and impervious in nature. When it becomes continuous and impervious in nature, it will block the movement, the diffusion of oxygen from the atmosphere to the alloy underneath, and it will prevent further oxidation. And the oxide scale should be able to flow plastically and self-heal cracks and discontinuities. So for this purpose, for all this continuous impervious nature, ability to flow plastically and self-heal cracks and discontinuities, there are certain properties which are important. And another important property is pilling bedwork ratio between 1 and 2. So when pilling bedwork ratio is basically the ratio of the molar volume metal oxide to the molar volume of the corresponding metal. So now if this ratio is too much, what happens? There is a volume expansion, there are compressive residual stresses, and there is cracking in the oxide scale. So oxide scale, if there are cracks, then it permits the cracks actually provide short circuit path for diffusion of oxygen into the underneath metal. However, if that is values greater than 2. If the ratio is less than 1, the oxide coating layer is too thin and it is discontinuous and it doesn't provide any protective effect. On the other hand, if it is in 1 and 2, the oxide coating is passivating and provides a protective effect against further surface oxidation. So this is what is important when we try to have a protective oxide coating. And so that's what happens in chromium containing steels, in titanium alloys, in aluminum alloys. Because alumina, when it goes on aluminum containing alloys, it is impervious. Similarly, in certain alloys which grow TiO2 or chromium oxide also, in ferritic stainless steels, chromium oxide forms an impervious layer, which acts as a diffusion barrier for oxygen. And that's why ferritic stainless steels are used at high temperature. So the oxide scales which are good for high temperature, up to 1000 degrees is chromia scale, which actually grows on ferritic stainless steel. And above 1000 degree, actually it is Cr2O3 from CrO3 gas. And that's why chromium containing alloys is not good for above 1000 degree. Above 1000 degree, only two scales are protective, which is alumina and silica. So alumina is crystalline, so it is not that good because grain boundaries provide short circuit paths for diffusion of oxygen, whereas SiO2 scale, which forms an molybdenum disilicide, silicon carbide, that is protective. That is amorphous in nature. It doesn't have any grain boundaries. Another option is borosilicate glass. Now, borosilicate glass has better added advantage because B2O3 has a lower melting point, and the borosilicate glass becomes soft at 1100 degrees centigrade or 1000 degrees centigrade. So because it becomes soft, it is able to heal the cracks very easily. So it is kind of self-healing nature. And so that's what I mentioned here in the previous slide, that about the ability to flow plastically and self-heal cracks and discontinuities. So this is observed in the case of borosilicate scale. So this is the Ellingham diagram, free energy formation versus temperature for different formation of different oxides per mole of oxygen. And you can see that the most stable is the one with the lowest free energy of formation, which is alumina. And silica, SiO2 and TiO2 are close. There is an overlap between them. And this over here is molybdenum trioxide, which is again actually becomes volatile at high temperature. And so there are other oxides in between. So this is the way it varies. So alumina followed by TiO2, followed by SiO2, followed by chromium oxide. So this alumina is the most stable, and chromium oxide is the least stable among these four, but there are others which are much less stable. And what is desirable is the least mass gain with increasing time at a temperature of exposure like 1200 degrees centigrade, and also a parabolic type of behavior where this relation is followed. Delta W square is the mass change in mass and with time is equal to Kp is a parabolic rate constant multiplied by time plus some constant. So you see the plots of W square versus T, which shows more or less a linear fit. So this shows there is a parabolic trend of behavior observed for molybdenum disilicide. So for other materials also, high temperature materials, this parabolic behavior, if it is observed, then we know that there is an oxide scale which has formed, and the kinetics is controlled by the rate controlling process is basically the passage of oxygen through the oxide scale from the atmosphere to the alloy underneath. So now if this is stable, if the oxide scale is stable, the behavior becomes parabolic. That means if further increase in time, the rate of oxidation decreases. Now these are parabolic rate constants for some of the oxides. You can see at the lowest one is SiO2 and the highest one is TiO2. So high parabolic rate constant means the growth rate of oxide scale is fast. For the oxide scale to be protective and stable and impervious, it is desirable that the growth rate is slow. In that case, the oxide scale is less porous. And that is why you see the growth rates of SiO2 and alumina at the slowest. So these are the oxide scales which are protective in nature, whereas TiO2 is not that protective. So factors affecting protective scale formation are concentration of stable oxide forming elements like silicon, aluminum, and chromium. So that means higher concentration will mean that the higher activity of these elements, and then the oxide scale formation is faster. And thermodynamic stability and growth rate of oxide scale constituents, which we already discussed. So it should be thermodynamically stable compared to other oxides, then it forms quickly and it is not reduced by other metals. And diffusivity of oxidizing species should be as low as possible. Diffusivity of oxygen in oxide scale should be as low as possible. These are the factors which are affecting the structure, crystalline or amorphous. So if it is amorphous, it is better. And ionic volume defect concentration in oxide scales. So suppose the oxygen anions move through the oxide scale. So if there is an anion vacancy, in that case, it will provide easier. It will make it easy for oxygen to pass through. But if there is excess anions, or in that case, the oxygen will find it difficult to pass through the oxide scale. So defect concentration is also important. So now the formation of volatile oxides like B2O3, molybdenum trioxide, and WO3. So these are problems with refractory metals like molybdenum and tungsten, because they form oxides which are volatile at high temperatures, and so they actually vaporize, and so there is weight reduction, and that leads to catastrophic oxidation. And then internal stresses caused by growth and volume changes due to phase transformations in oxide scale, and thermal expansion mismatch between oxide scale and the substrate, which leads to internal stresses. Due to stresses, there are cracks, and that leads to further oxidation. So this is particularly observed when there are cycles of heating and cooling. So now to replace nickel-based superalloys in aero engines applications, so people have worked on refractory alloys, which are molybdenum and niobium based. And these are some commercial alloys, TZM and C103, which have been used even in Apollo 11 and many other applications. But they are good in space. Their oxidation resistance is poor. And then so particularly above 1000 degrees centigrade, above 1100 degrees centigrade. The tungsten, chromium, niobium is good below 1000, but above 1000 it is not good. Then these are refractory multi-component alloys or complex concentrated alloys or high entropy alloys being developed. and they also have poor oxidation resistance at high temperature. So option is refractory intermetallic silicide, molybdenum silicon based or niobium silicon based, which my group has worked on, and ultra high temperature ceramic composites like zirconium diboride, hafnium diboride based composites, carbon fiber, silicon carbide, and CFSiC, GrB2SiC composites. So this shows the different the chronology of development of nickel based superalloys with so up to 2000 and 2010 or so, the single crystal, third generation single crystal alloys have been developed. People are now, so they have a large number of alloying elements, and so still the temperature is about 1150. So above this temperature, these are the options: molybdenum silicon boron type alloys or niobium silicon type alloys. And main requirement is to ability to retain the strength with oxidation resistance, but with acceptable fracture toughness. So this is the challenge, because the moment we increase the strength, we get good high temperature strength retention and oxidation resistance. The room temperature fracture toughness is compromised, and vice versa. If the room temperature fracture toughness is improved, we lose oxidation resistance and strength retention. So these are certain problems which we are talking about. So this is a molybdenum silicon phase diagram. You see there are three intermetallics in this system: MO3Si, MO5Si3, and MOSI2. Actually, these arrows have slightly moved. So MO3Si is here, MO5Si3 is here, MOSI2 is here. And these are the crystal structures. You can see the crystal structures are quite complex. The melting points are very high, but their fracture toughness is very low, between 2 to 3 MPa root meter or 2 to 4 MPa root meter. And the brittle to ductile transition temperatures are also very high. And they don't have 5 independent slip systems, which you all metallurgists know, that which is essential for a polycrystalline material to be ductile. And they have ordered structure, so and as a result, the Pearl stress is also very high. So to mitigate this problem, people have gone into the molybdenum silicon boron ternary system. So in these ternary systems, actually, there are 3 phases which are stable. The alloys with this kind of compositions. We have molybdenum solid solution phase, because it's metallic solid solution, it gives toughness enhancement. Then we have 2 intermetallic phases, MO5SiB2, which is very hard, and its grip resistance is very much superior to all intermetallics. And MO3Si and MO5SiB2, because they contain silicon, and this one contains silicon and boron, their oxidation contributes to the formation of borosilicate glass, and they protect from oxidation. So this is a typical microstructure of MOSI-B alloy, where we have MOSS, MO3Si, and MO5SiB2, which is T2 phase. And this was prepared by powder metallurgy process by hot pressing at 1600 degrees centigrade. And this is a typical load displacement curve done by one of my MTech students. He observed that the load drop, which is normally for brittle materials, will come down sharply, but here it is arrested. And then the actual load increases in between, and then there is a gradual decrease in load after some time. It goes to a maximum. So that means the crack has hit a molybdenum solid solution particle, a molybdenum solid solution phase, which is ductile and undergoes work hardening. So there is an increase in the load, then it goes gradually decreases. And this is an indentation crack. This is Wigger's indentation forward, and there are cracks. You can see the crack gets blunted or arrested by the ductile phase. And we found measure of residual strength, fracture toughness. And so fracture toughness is in the range of 5 to 6 MPa root meter, which is also not very high. We need around 15. And but the oxidation resistance, which we studied in the range of 500, 1300, we found that if you do at 500, 600, it is fine. But if you do at 700, there is a continuous loss in mass, because molybdenum trioxide forms, which vaporizes continuously, and there is loss in mass. But at a higher temperature, like 800 and above, There is mass loss in the beginning because molybdenum trioxide forms, but then once it goes away, after some time, the borosilicate glass shell forms, which is shown here. Silicate is SiO2. So basically, that protects the oxide scale underneath alloy, and that is why there is no further oxidation. So that happens. So there is a stable regime coming, and that happens more quickly at 1150. So the growth rate of SiO2 is, as we saw, it is slow. So at lower temperature, diffusivity of silicon is also less. So that's why at below 1150 degrees centigrade, it grows slowly. But at 1150, it grows quickly. So we saw minimum mass loss at 1150. And we also found that if you hold at 1150 for some time and then you hold again at 700 or 800, you don't see this kind of behavior. That oxide scale that is found at 1150 protects from further oxidation even at other temperatures. So it is a good idea to pre-expose the alloy at 1150, form a protective oxide scale, and then you subject to other temperatures. This was the conclusion from this paper. So then we did high temperature compression test, and this is molybdenum silicide from two different sources. One is reactive hot pressing, one is obtained from AC Struck, Germany. We hot pressed them, and this is ammonite SiC. This is molybdenum silicon boron alloy, the composition that I was talking about, and this is a niobium silicide based alloy. We found that the molybdenum silicon boron alloy retains strength at high temperature the best. So that strength retention property is very good, its oxidation property is very good. Only drawback is low fracture toughness. So another option is niobium silicon system. So here we have two phases, NBSS, niobium solid solution phase, and NB5Si3 in binary system. If you go to complex ternary systems, then we also get Laves phase. So this kind of alloys are developed by where we have niobium, titanium, hafnium on one side, silicon, aluminum on the other side, and chromium on the other side. So these kind of alloys are developed by General Electric in USA, G, and so there are three types of phases. At IIT Kharagpur, we have, of course, we worked on niobium silicon molybdenum alloys, about which we'll be talking about. And so in G, there was extensive studies, and they have done analysis of Lassa-Miller parameter, basically the stress rupture behavior. And they found that the niobium, titanium, hafnium silicon based alloys are somewhere here, that is superior to fourth generation nickel based super alloys. Of course, not as good as the TZM. But again, these have slightly superior oxidation resistance compared to TZM. And these are the single crystal blades of niobium silicide, of directionally certified blades of niobium silicide composite. So these have been also tried. But again, there is a property, there are some problems, so that's why they are not still in use. But the relative density is similar to that of nickel based super alloys. People in China are also working on this. They're growing these alloys by nickel directional solidification. So in our research group, we have worked on niobium silicon molybdenum alloys. The first PhD was Kaushik Chattopadhyay. So we added molybdenum as alloying element to niobium silicon based alloys, and we found that additional molybdenum inhibits the formation of NB3Si. It stabilizes the beta NB5Si3 that is phase, and it creates solid solution sending of NBSS and makes the diffusion sluggish. In fact, that helps in improving oxidation resistance, we'll see. So you can see that in this alloy, we have nonlinear as a non-lamellar eutectic, which is kind of coarse in nature, and the eutectic forms has a niobium solid solution phase, which is ductile, and NB5Si3 phase, which is brittle. So this ductile phase, it doesn't allow the cracks, it blunts the cracks. So that's why you see the crack is actually, it bridges the crack. So this becomes discontinuous. It gets blunted within the ductile phase. And so that actually helps in toughening. Also at high temperature, you can see that alloys with higher molybdenum content, they shows higher strength retention, both yield strength and maximum stress. This is observed for hypereutectic alloys, not for the hypereutectic alloys. Why? because the hypoeutectic alloys have niobium solid solution phase as the primary phase, whereas the hypereutectic alloys has the silicide phase as the primary phase, which is brittle in nature. So their solid solution setting is not observed. But in the metallic phase, in the alloy phase, because this is primary phase is NBSS, so that is strengthened by molybdenum, and that is why we see the effect. There is a solid solution strengthening. So this alloy is 13 silicon, 4 molybdenum. This is 12 silicon, 15 molybdenum. So with increase in molybdenum concentration from 4 to 15, this is the increase in bulk concentration. The amount of molybdenum dissolved in NBSS is also higher, gets higher, and that's why we get higher strength here. So that shows the solid solution strengthening. And we looked at the oxidation behavior of the niobium silicon molybdenum alloys. We found again interestingly that to increase in molybdenum content, the weight gain was reduced. So even the hypoeutectic alloys, which are supposed to be more oxidation is supposed to be less, also showed for higher molybdenum content, it showed lower mass gain. So then we wanted to see why it is so, because we expected otherwise, because hypoeutectic alloys have less silicon. So naturally, we expected oxidation rates to be worse. But then higher molybdenum content lowered the diffusivity, and that's why the oxidizing species diffusion to oxide scale was reduced. And so that permitted the growth of SiO2 scale at the interface between the outer scale and the alloy underneath. And this SiO2 scale was continuous, and that probably contributed to the oxidation protection. Additionally, molybdenum lowers the anion vacancy in N2O5. So because anion vacancy concentration is decreased, so the ability of oxygen vacancies, oxygen ions to penetrate, because when there are a lot of vacancies of anions, oxygen anions can pass through Nb2O5. But if the anion vacancy concentration is reduced, in that case, actually the oxygen is not able to penetrate the Nb2O5 scale. And why? Because molybdenum is tetravalent and niobium is pentavalent. So when molybdenum is doped into Nb2O5, it lowers the anion vacancy. So in my next student tried addition of titanium in the NBSI MO alloys. So we added 20 titanium to both hypoeutectic and hypereutectic alloys, and these alloys are prepared by arc melting like the previous alloys. But here we annealed some of the alloys at 1500 degrees centigrade for 100 hours in inert atmosphere. And we see that in these alloys, in the fast cast alloys, we have both lamellar and non-lamellar eutectic. The hypoeutectic microstructure contains primary NBSS and eutectic. Eutectic contains NBSS ductile phase and 5,3 silicide, which is a solid solution of niobium, molybdenum, and titanium and silica, and with intermetallic silicide. Hypereutectic contains primary silicide phase, which is brittle, and then eutectic contains mixture of ductile and brittle phases. And then we have beta titanium solid solution phase in the titanium containing alloy. So on annealing, we found that a microstructure got coarsened, and we found more amount of nonlinear eutectic in the titanium containing alloys. So as a result, what happened was the hypoeutectic alloys have shown higher fracture toughness. You see this fracture toughness, and the hypereutectic alloys have higher fracture toughness than the corresponding hypereutectic alloys. So why I am calling this hypoeutectic? Because if you look at the original phase diagram over here, sorry, yeah. So the eutectic is at 17.5 atom percent silicon. So naturally lower than this is hypo, higher than this is hyper. Sorry. Yeah. So these are hypoeutectic alloys. They have shown higher fracture toughness than the hypereutectic alloys because NBSS is the primary phase, which is a ductile phase. And annealing has converted lamellar to non-lamellar eutectic, and that's why on annealing the fracture toughness is increased. So all those marked as HT, those are annealed conditions. So they have coarser primary phase. So you can see that the fracture toughness has gone up to 14, more than 14 MPa root meter. So we have almost achieved the minimum fracture toughness of 15 MPa root meter, which was the target to be achieved. And this is actually because the crack parts undergo deviation because they cannot penetrate the Navium solid solution phase. So they pass through the interface between NBSS and NB5SI3, and they also get blunted by the NBSS phase, which is a ductile phase. And high temperature compressive strengths are determined. When room temperature compressive strengths are also determined. We found that the strength retention was better for the hypereutectic alloys compared to hypereutectic alloys. Although at room temperature, the hypereutectic alloys shows higher strength, compressive strength and compressive strength, but at high temperature, the hypereutectic alloys actually showed higher strength, again because of solution strengthening due to the molybdenum addition and titanium addition. And oxidation resistance was observed, we found this is non-isothermal oxidation exposure where we did heating. So titanium containing alloys showed lower mass gain compared to alloys without titanium. And that also was, this was here, heating was done up to 1300 degrees centigrade in a differential thermoanalyzer with thermogrammetric analyzer. And here actually we expose it inside a furnace for different durations up to 24 hours. And it was isothermal at 1200 degrees centigrade. So we found that the mass gain was the lowest for the alloy, which is hypereutectic and with 20% titanium. So what is titanium doing? Even in the oxide scale, we found that titanium addition led to smaller oxide scale thickness. So it basically arrested the oxide growth. So oxidation resistance, that means we concluded that oxidation resistance increases with silicon content because hypereutectic alloys have shown superior oxidation resistance compared to hypo. And we have also observed lower mass gain on addition of 20% titanium. And the reason we have found, scientific reason, is that the titanium oxide and SiO2, they have peeling bedrock ratio between 1 and 2. So whereas the peeling bedrock ratio of NB2O5 is greater than 2. So that actually reduces the stresses. So we have basically here an outer layer of NB2O5 and TiO2 and an inner layer of TiO2 and SiO2. Now this TiO2 SiO2 inner layer has lower peeling bedrock ratio, and it is actually continuous, and it protects from further oxidation. So ternary niobium titanium oxide is found on the titanium containing alloys outer side, which is confirmed by the X-ray diffraction also. And we also saw parabolic rate lobbying observed after initial period of exposure. And here also it is so because of the protective nature of the oxide scale. So this again confirms that oxide scale is protective. And addition of zirconium and gallium to hypereutectic NBSI MOTI alloy improved the fracture toughness further to almost 15 MPa root meter. So particularly for zirconium containing alloy, and although it is hypereutectic, you see, if it is hypereutectic, it would have been much more. But because they didn't show enough oxidation resistance, we chose hypereutectic alloys. And by adding 3 atoms of zirconium, we found that it improved further. We went into the mechanisms of this and we published it. So basically, it increased the NBSS content, and the fracture toughness improved significantly. Even the high temperature strength increased. Very rarely you see both strength and fracture toughness increasing. Normally, if strength is increased, fracture toughness decreases. But in this case, we saw high temperature strength increasing and room temperature fracture toughness increasing simultaneously. And even the oxidation resistance improved under certain conditions, under certain temperatures. So zirconium addition is a good idea. Gallium addition didn't actually contribute to oxidation resistance. Of course, it helped in improving both fracture toughness and strength. So directions of future work for silicides is that the scope, there is scope for improvement in high temperature strength, room temperature fracture toughness, and oxidation resistance by alloying, and a computation approach will be helpful where actually one can predict the microstructure and properties with, and then do experimental validation. And so such approaches are being, Calford-based approaches are being used now these days. And there is an effort to develop protective and self-healing coatings by pack cementation of aluminum or siliconization process to improve oxidation and hot corrosion resistance. So this is silicon, boron-silicon coating type is added, is applied so that borosilicate scale can form on silicide, on molybdenum and aluminum silicide of any composition. So this this kind of approach has been developed by Professor Perepeshko of University of Wisconsin-Madison in USA and his group. So now I'll be talking about ultra-high temperature ceramic composites, focusing on zirconium diboride silicon carbide composites, carbon fiber silicon carbide composites, and CF-ZrB2 SiC composites, which we have worked on. So why ZrB2 and HFB2? Because you can see the melting points above 3000 degrees centigrade, and that is why they are called ultra-high temperature ceramics. And density of ZrB2 is actually not much. Of course, HFB2 is very high, 11.1, but ZrB2 is not much. Elastic modulus is quite high, near 500. Hardness is also very high. Flexural strength is also quite high, but fracture toughness is low. And again, one problem is that oxidation resistance is not very good above 1000 degrees centigrade, because ZrO2 also forms a porous oxide, and B2O3 as a liquid, it tries to protect on up to 1000, but above 1000, ZrB2 oxidation resistance becomes very poor. So silicon carbide is added as a reinforcement so that a silicon carbide will form SiO2 and ZrB2 will form ZrO2 and B2O3. So B2O3 and SiO2 together forms a borosilicate scale which protects from oxidation. We'll see that little later. So major challenges in making ZrB2 SiC composites is because of the low ionic diffusivity at elevated temperatures, because they have very high covalent nature. And they have also oxide impurities on their surface, which basically because of that there is less atomic scale contact when you try to sinter them at high temperature. And as a result, there is grain growth and degradation of properties. These oxides actually sometimes they form a liquid phase and they result in anomalous grain growth rather than densification. So the processing methods are pressureless sintering. It is desirable for near net shape processing, but densification requires use of proper additives to reduce the oxides impurities on the surface and to limit grain growth. And other option is hot pressing, which is desirable for achieving a high density, and it is applicable for processing simple shapes only. So that is a disadvantage. Spark process sintering is another process which is desirable to maintain finer grain size by reducing processing temperature, but it is difficult to process large or near net shapes by SPS, which is a short form of spark process sintering. So we developed a pressureless sintering process in our lab. It was work was done by one student, Manav Mandi, and so he worked with ZrB2 10, 20, and 30 and 40. One was a silicon carbide. The powders were mixed by ball milling, and we added phenolic resin as a source of carbon, and ZrB2 boron carbide was taken as an additive. And initially, after mixing the powders, these are cold pressed at 100 MPa. Then it was taken to a furnace where it was held at 850 degrees centigrade for 1 hour to get rid of the phenolic resin. The volatile components went away, leaving behind carbon. Then it was held at an intermediate temperature at 1250 and 1600 for half an hour, and then sintered at 1950, 2000, and 2050 from the periods from between half an hour to 3 hours. And ultimately found that at 2000 degrees centigrade, we get the best density, best results. And the reason why we did intermediate temperature holding at 1250 and 1600, as I mentioned, is because certain oxides, which are the main culprits like B2O3 and ZrO2, SiO2, they are reduced by carbon or B4C at certain temperatures. So this is the free energy change versus temperature diagram. And at temperatures where the free energy change becomes negative, those are the temperatures where its reaction is feasible, its reduction reactions are feasible. And that is why this intermediate temperature holding was done. And we also found, because we did tungsten carbide, used tungsten carbide vials and balls for milling in the ball mill for mixing, there was some tungsten carbide impurities. And so tungsten carbide also helped in reducing the oxide impurities, and it left certain tungsten and which was this tungsten carbide cobalt, tungsten cobalt type impurities in the powder. And when we did the pressureless sintering, we found there was a tungsten rich boundary phase which are formed over here, and the grains are rounded in shape. So that shows that a liquid phase may have formed because we did at 1000, we sintered at 2000 degrees centigrade and in vacuum. So a liquid phase may have formed, or not in vacuum, inert gas. So a liquid phase has formed, and that's why it has weighted the ZrB2 grains. So that's why there is basically a rounded kind of, there's partial dissolution. So that's why there's a rounded shape. And the pressureless sintering, I've already discussed this. These are the results. Relative density has been plotted as silicon carbide content. So you can see that the density has increased with 0% silicon carbide. Only 83% densification could be achieved. At 10%, we achieve between 90 to 96%. The best one for intermediate with intermediate holding, half an hour, and intermediate holding, which is the pink one. And without intermediate holding, densities were less. So intermediate holding actually helped in reducing the oxides impurities that helped in addition and densification. And you can see the for 20 and 30 and 40 volume percent, the density kept on increasing. So from above 98 to nearly 99.5 or 100%. And similar behavior is observed for micro hardness also of ZrB2 phase. So naturally, so that shows that the silicon carbide addition amount, so that also helps in densification because it helps in reducing oxide impurities. And we found by measuring thermal conductivities and thermal diffusivity that a composite with 21% silicon carbide showed the highest thermal diffusivity. And the thermal shock resistance we measured by doing indent, taking an indent, a Vickers indent, and looking at change in crack length on heating to 800, 1000 and 1200 for 15 minutes, and then quenching in water. So rapid cooling was there, so leading to thermal stresses. And we found that this reduction in the least increase in crack length and least reduction in hardness. We also measured Young's modulus. So least reduction in modulus, hardness, and least increase in crack length happened in the case of 21% silicon carbide, which also showed the highest amount of thermal conductivity among the pressureless sintered composites. This is a result obtained for hot press composite. You see, it is even higher because this composite had a slightly higher density and different grain size. So it showed different kind of behavior. So it didn't have the other impurities like boron carbide, and so that's why its thermal conductivity is higher. So that's why 24% silicon carbide is considered to be optimum for other kind of studies. So now this is hot press ZrB2 composites, HrB2 composites, and we have also worked with zirconium diboride, silicon carbide, silicon nitride composite, and zirconium diboride, zirconium carbide, silicon nitride. Now these composites showed better ablation resistance. What you see, the fracture toughness was, and high temperatures and strength, everything, that was the best for the zirconium diboride, silicon carbide, silicon nitride composite. But we found that the high temperature creep resistance of this composite was not good. So that's why focus on zirconium diboride, silicon carbide composite. We also prepared composites by addition of lanthanum hexaboride, and in addition to boron carbide and carbon by spark process sintering. Without lanthanum hexaboride addition, we could not get density by spark process sintering. On lanthanum hexaboride LaB6 addition, we found that these acted as a scavenger for oxygen, and they formed lanthanum borate, etc. And these are the grains. So grain sizes are much finer because here the sintering was done at 1600 or 1800, not at 2000. So when you do something at lower temperature, there is less amount of grain growth, and the silicon carbide particles uh, they don't permit grain growth. Similar thing also observed pressureless sintering. Silicon carbide particles between the grain boundaries don't allow the grains to grow, and that actually increased the hardness in that case. Here also we saw a similar kind of behavior. And very recently we have tried another technique, gel casting of green bodies followed by pressureless sintering. Here we have used egg white, which is basically which contains ovalbumin protein as a binder instead of phenolic resin, which is actually hazardous. And additionally, we have added sucrose to control viscosity, and we have made a slurry with ZRB2SiC. And we have used polyacrylic acid, which has dispersant, a small amount, and 1 octanol, very small amount of that as anti-foaming agent, so that addition of egg white doesn't lead to any kind of foaming during mixing. And we prepared a liquid premix, which we added to ZRB2SiC powder, made a slurry. And we actually optimized the composition of the slurry by different geological experiments, which details of which I'm not showing. And after that, we did gel casting into different molds. We got the green body, which had sufficient amount of strength and about more than 50% green density. So these are the green bodies. And these are basically, you can make any shape because you're doing by casting, and it is casting of a slurry. It is possible to make any complex shape in even larger pieces, which is not possible to make by cold compaction in a uniaxial press that we did initially in Bhubaneswar. So this is the work of Virushni and Sunil Kashyap. So then we sintered them at 2000 degrees centigrade with prior holding at 1250 and 1600 at day model furnace. And then we could get almost certain densities were close to 98%. So we could make big pieces of ZRB, so 100 by 100 into 5 mm. So these are because we promised in the DRDO project that we will be making tiles of this size. So we could make that. We could make green bodies and sinter them, and we could get density of 90%. And particularly when you had boron carbide and boron carbide as an additive, in addition to phenolic resin, in addition to egg white binder, which actually, see, egg white and other organic products, they burn out during the heating because we are doing something at 2000. So they burn out during heating, but they leave behind carbon. So that carbon actually reduces the oxide impurities. And then we could get sintered densities like this, and we have boron carbide, ZRB2 and SiC. And hardness is between 14 to 16 Vickers hardness, HV, Vickers that is the number. And fracture toughness between 4 to 6 MPa root meter and Young's modulus of 474 GPa. So these were actually measured products. We also did X-ray microscopy imaging. We found that for certain compositions, so sucrose was less or not added. Here S00, sucrose was not added. A lot of porosities were there even after sintering. So this is where we had a composition of slurry composition of 35% solid loading, that is ZRB2SiC, egg white 22% volume percent, and sucrose 8 volume percent. So we saw very little porosity, good densification was there. So slurry composition we found plays a critical role in the densification process. And we looked at the oxide scale formation. We found that the inner scale of zirconium dioxide is there and outer scale of borosilicate is there, which is protecting at 1200, 1300, even at higher temperature, 1400, 1500. In the case of lanthanum hexaboride containing scales, we got multi-layered scales with different layers. And so basically, the scale containing borosilicate glass over here, that provides protection from further oxidation. The behavior was parabolic, as you see. These are 1300 degrees centigrade. We did cyclic oxidation at 1300, 1400, 1500, and we found that the best oxidation resistance was obtained for the composite with the highest amount of lanthanum hexaboride. As I showed in the previous graph here, that the lanthanum hexaboride content was right from 7 to 14 volume percent. So in the oxidation resistance, we found that the best oxidation resistance obtained for the highest lanthanum hexaboride, the mass gain was the least. at all the C temperatures. And so there is a lanthanum silicate scale outside forming, and this is continuous at higher lanthanum hexafluoride content. And this is a refractory oxide type nature. It is very protective. Then we looked at the ablation behavior. So here we have an oxyacetylene flame, which is aimed at ZrB2 composite sample and is embedded in a graphite piece. And the flame temperature was 2000 degrees centigrade and the 2200 degrees centigrade front face temperature. The back face temperature was measured using a thermocouple, and we got about 500 to 600 degrees centigrade back face temperature. So there was actually a temperature gradient of 600 to 700 degrees centigrade, and the exposure was up for a duration up to 15 minutes. And we found that the ZrB2 SiC composite showed the least mass gain and least reduction in Young's modulus after the ablation treatment. Then we looked at the oxide surfaces. We found the surface of the ZrB2 SiC composite to be least porous, and it showed ZrO2 and ZrSiO4 formation. So then we tried to analyze the results, and we found that this less loss in properties as well as the stable oxide scale indicates that ZrB2 SiC composite has the best ablation resistance, and it also has got the best thermal shock resistance. So that's why this 20 SiC composite was chosen for our further studies. The main problem in this composite is that it has got poor fracture toughness, it has got catastrophic and unstable failure, and thermal shock resistance is also not very good. So what is the solution? Solution is to design and develop continuous fiber reinforced composites. So why develop continuous fiber reinforced composites? So this is a schematic, this is a matrix, ceramic matrix, in which there is a continuous fiber of carbon or silicon carbide. So whenever there is a crack, which passes through the brittle ceramic, it comes to the fiber matrix interface. Now the interface is engineered in such a way that is weak. So the crack tries to get deviated and pass through the interface. So as a result, it becomes kind of a tortuous, the crack path becomes tortuous. And then somewhere again, the fiber is taking the load, and somewhere the fracture fibers, the fiber is fractured, and again it passes like this. So because the crack path becomes tortuous, there is a lot of deviation from linearity. If the crack path would have gone straight, the load displacement curve would have been straight like this. It should have gone up and come down. But here it doesn't happen. It goes up slowly and it deviates from linearity and comes down gradually. So to do this, actually, in our work, which was the work of my student Ramya, so in INAE Bangalore, they have developed a technique where they coat these layers of pyrotic carbon and silicon carbide on the carbon fiber. Then they make and after that they infiltrate with silicon carbide. So what it actually ensures a weak interface, and it also lowers the interfacial compressive stress after cooling of from high temperature processing. So you can see the stages of development of carbon-carbon composites. 1970s it started, and then 1980s people came up with carbon fiber silicon carbide, silicon carbide, and it was made by liquid silicon infiltration to make silicon carbide in situ on the carbon. And then so basically this was reactive processing, and then in industrial production of CMCs happened, and this was CFSiC composite was used in SNECMA by French people, and this was actually done by chemical vapor infiltration in 90s. And so people came up with SiC or CFSiC brakes for aero engines because of their wear resistance and hardness. And there was focus on understanding microstructure property correlation. And so these are the specific applications like gas turbine components like seal rings designed for rotation engine shaft, low pressure turbine jet vents, turbine shrouds, and then nozzle flaps, combustor liners, flame holders, exhaust cones, engine flaps for military jet engines. So this was the application which was we had an ARDB project. Actually, this was what we intended to do. The application temperature was 1250 degrees centigrade, according to GTI. So two kinds of composites are prepared at NAL. One is having 2.5D, where we have two perpendicular rows of carbon fiber and stitched in the vertical direction. And here we have three different orientations of carbon fiber. So this was made by 8 layers of 8H 13V carbon fiber, one upon another, and then stitched along the Z direction. So this is 8 layer, this is 8 layer, and the carbon fibers in perpendicular directions with respect to each other. And these are stitched in the Z direction. And here, actually, we have 3D carbon fiber prepared by moving binding of orthogonally oriented carbon fibers. And so preform preparation was done, and then it was held in high temperature graphite cathode. Interface was coated with biotic carbon silicon carbide multi-layers by chemical vapor deposition. And then SiC was infiltration was done. Then after that, it was machined, and then it was SiC seal coated with silicon carbide to provide, because surface was porous and rough. So silicon carbide was deposited by chemical vapor deposition, and then the final carbon fiber silicon carbide composite was obtained. So basically, this is the these are the reactions. Basically, in chemical vapor infiltration, gases like trimethyl chlorosilane gas, hydrogen, boron carbide, methane, these are introduced, and there is a reaction, in situ reaction, where carbon, silicon carbide, these are formed in situ. And so even we get SiC, silicon boron carbon can be deposited by having reaction between methyl trichlorosilane and boron BCl3. And similarly, methyl trichlorosilane reacts with hydrogen to form silicon carbide. So basically, silicon carbide matrix is deposited in situ. SiBC matrix is also deposited in situ at high temperature and inside a reactor, CBI reactor. So this facility is there in National Aerospace Laboratory and DMRL Hyderabad in India. Only two places. So we got composites with density up to 2.14 in the case of 2.5D and 3D 2.08. So 3D composite actually has higher density, higher porosity content, but 2.5D has slightly higher carbon fiber volume fraction, and it has got along X and Y direction close to 50% of carbon fibers volume fraction, and along Z direction, that is stitching direction, only 0.5%. Whereas 3D carbon fibers are distributed in all three directions, 30% in X and Y and 40% along the Z direction. So this is the microstructure. You can see a lot of pores in the 3D, which you cannot see it is there in 2.5D also, but smaller amount, and these are interbundle pores. And here we have interbundle pores, which are looking like this between the fiber bundles. And we also have interfiber pores. So to look at the porosity, we have done X-ray microsity, and this was done in IIT Kharagpur, and this was done in University of Warwick. So in 2.5D composite, we have interbundle pores mainly at fiber cream positions, and 3D composites, we got regular fiber arrangement with uniformly distributed pores, and fiber orientation strongly governs the pore distribution orientation. We can see the nature of pores is defined for 2.5D and 3D composites. And so we have quantified the distribution of porosity, and we have published the results also. So now this is silicon carbide SiC seal coating and SiBC, and then carbon fiber silicon carbide composite. This is a cross section of carbon fiber surrounded by SiC, and average carbon fiber diameter was 6.4 micrometer. SiBC layer here is about 7 micrometer. SiC seal coating was of 26.3. So SiC seal coating actually helps in improving the oxidation resistance of this CFSiC composite. And SiBC actually, even if the SiC seal coating gets oxidized, the SiBC forms oxidized from a borosilicate scale, which is self-healing in nature. So this is the reason why SiBC is deposited beneath the SiC seal coating. And we looked at the PIC is carbon interface between carbon fiber and silicon carbide matrix, and we could see using TEM, and the samples are prepared with focused and beam, and transmission electron microscope could resolve the interface between carbon fiber and the silicon carbide, which contain pyrotic carbon, which is deposited by chemical vapor infiltration and deposition. And we found that we looked at the fracture toughness in crack arrestor mode. Crack arrestor mode is basically where a notch is cut perpendicular to carbon fiber layout, and here crack divider mode, the notch is along the carbon fibers. And the crack divider mode, the fracture toughness was less, but at crack arrestor mode, it was nearly 16 MPa root meter. You can see quite high. And 3D composite showed nearly 19 or 20 MPa root meter fracture toughness. So that is far better than what we got for ZRB2SiC, that was between 5 to 6 MPa root meter. And presence of SiC seal coating without, we did flexural test in composites and without seal coating. We found that with seal coating, we got superior flexural strength, and 2.5D composite showed superior flexural strength compared to 3D composite. Again, because of higher volume fraction of carbon fibers, more anisotropy, and along the tensile direction, we have more carbon fibers of 2.5D, higher volume fraction, like close to 50%, and for this maybe 30% or 40%. So naturally, the 2.5D composite showed higher better properties. And crack propagation through the layers was delamination. We saw delamination in the case of 2.5D composite, because here we had laminates of layers of 13 weave SiC fiber forms, which are stacked in vertical direction and stitched. So there was delamination kind of a thing. But here, because the carbon fibers or 3D composite carbon fibers are aligned along 3 different directions, so it didn't permit delamination. So Z direction fibers helps in binding X and Y direction fiber, and that, so there was better fracture toughness as a result. Here the fibers are load bearing. We looked at the tensile behavior, and unlike metals and alloys, the tensile strength increased with temperature. And that happened for both 2.5D and 3D composite. And that was interesting. And so we got lower tensile strength for 3D composite compared to 2.5D. Similar strength for flexural strength. And strength and tensile strength was measured from 28,000 to 1250. And we also did thermal cycles between 80 to 1250, 30 times in a furnace. And then we measured the tensile strength. We found that there is a superior tensile strength retention in the case of 2.5D composite compared to 3D composite. So it was 99% strength retention, you can see, for 2.5D and 78% for 3D. So we tried to understand the results. And so why tensile strength increases with temperature? So we found that we looked at the carbon fiber peak and in X-ray diffraction, by high temperature X-ray diffraction, we found that they become sharper with increase in temperature, as you can see here. So that showed that this is basically the basal peak of carbon fiber. So the basal planes gets oriented in textured, which is the strongest direction of carbon fiber along the axial direction, and that this would strength increase, and that has been also reported by others. Another thing is that the thermal stress gets reduced, and self-healing, the borosilicate scale, the SiBC oxidizes to form a borosilicate glass, which heals the cracks at high temperature. So naturally, we got strength increase at high temperature. And we also found that the fiber matrix debonding also increased with temperature. We looked at the fracture surfaces, the 27,000 and 1250, and experimental observation showed that fiber matrix, the amount of fiber debonded from the matrix. So debonding happens by sliding of fibers in the matrix, which requires higher energy, and so that was more in the case of higher temperature. And that is again due to reduction of thermal residual stress, which actually there's a compressive stress introduced when you heat, when you process high temperature and then cool it. So that gets relaxed at high temperature, and so that's why debonding becomes easier. And also borosilicate glass forms at the interface, and that also allows sliding, interface sliding. So more debonding is observed, and so the fiber pull-out length actually increased with increase in temperature. And this is the confirmation of borosilicate glass formation by energy dispersive spectroscopy and XPS analysis, as we claimed on previous slide. We also measured elastic constants of the broken parts at three different directions. So interestingly, we found along the carbon fibers, the elastic modulus reduction was more. So carbon fiber directions are C22 and C33. So these are the compliance, these are the stiffness tensors, which was measured by, we had a measure equipment, ultrasonic phase spectroscopy, which we have used. So we see that along with increasing temperature of cycling, we see there is a reduction of elastic modulus along the directions of C22 and C33. These values decrease. These are directions of fiber. So that means there is more damage because fiber pullout happens. On the other hand, on the direction which is perpendicular to fibers, where only the SiC seal coating is there and SiC matrix is there, there is not much change in the elastic modulus. So that shows that it is basically the damage is also anisotropic. It is more toward in the direction of carbon fibers because of the fiber pullout and oxidation of the fibers. So now, very recently, in collaboration with DMRL, I have a student, Adarsh Ranjan Mishra, who is working on a hybrid composite. So we are basically, we have seen ZrB2SiC composites of poor room temperature fracture toughness, but they have good ablation resistance. Carbon fiber silicon carbon composites have good superior fracture toughness, high temperature strength, damage tolerance, etc. But their oxidation ablation resistance are not so good because SiC undergoes active oxidation at temperatures of 1500 degrees centigrade. So we have tried to fabricate CF ZrB2SiC hybrid composites. Let us see the rest of the story. We are almost towards the end now. So we have made fabric of carbon fiber, and then these have been actually coated with ZrB2SiC slurry and then put together and then hot pressed in the hot press. And these have been prepared. There are unidirectional carbon fibers, which is 0, 0. Then unidirectional carbon fibers, where fibers are oriented 0 degree and 90 degree. And then 13 wave carbon fibers infiltrated with ZrB2SiC. So these are the microstructures we have observed, and we have observed them in using after hot pressing. We saw how the ZrB2SiC is distributed in X-ray microscopy. And again, there is not much time to discuss those things. Now to infiltrate the ZrB2SiC more easily, we have ultrasonic. We have performed ultrasonification of the ZrB2, that is the carbon fiber preform, and so that the fibers come apart and infiltration is easier. It was also done by heat treating of the carbon fiber preform, and then ZrB2SiC infiltration was found to be better. And but on heat treatment, we found formation of zirconium carbide also. And so and the porosity content actually decreased because on ultrasonification or heat treatment, because the ZrB2SiC infiltration was better. And you can see that the strength was best for the as received, but on ultrasonification or heat treatment, actually the strength decreased because there was some damage to the carbon fibers. So it is basically, if you do one thing, you get better ZrB2SiC infiltration, but strength decreases. So you don't gain in every way actually. But then we looked at the work of fracture, we found that the heat treated carbon fiber preform showed higher work of fracture. That means work of fracture was actually obtained by calculating the area up to half the area of the peak over here in the load displacement curve. And because the fracture initiated somewhere here. So for that, how much energy was consumed, that gave us the work of fracture, the crack tip. The crack actually didn't progress fully, but there was sufficient bend, and the crack part was actually very much zigzag, which we did, again observed in the X-ray microscopy. Some other time maybe I will, I mean, in this presentation I've not included that result. We also did oxygen flame test, and we followed ASTM standards this time. And sample dimensions were 30 into 30 multiplied by 7.5 millimeter. And it was an oxidizing flame of oxygen and acetylene gas. And sample to nozzle distance was 90 millimeter. Heat flux was about 800 watt per centimeter square. So we found that formation of zirconium dioxide on the surface, in the case of CFZW2SiC. In the case of CFSiC, actually it formed, the damage was more severe. You can see this much has been lost. Here, the damage depth is much less. So you see that by adding ZW2SiC slurry, although we lose in terms of fracture toughness, but we gain in terms of ablation resistance. The damage depth is significantly reduced. So you can see ablation depth here is only 8.9 and 16.2. And here it is 46.3 for the same amount of duration of CFSiC. So this is actually 3 times more compared to, and here also it is 3 times more. So there is significant improvement in ablation resistance on infiltration of ZW2SiC slurry into carbon fiber silicon carbide composite. So that is the reason why this work is justified. And we also looked at the oxidation products, and we found zirconium dioxide has formed. And this is what the X-ray diffraction results. So zirconium dioxide, actually we have seen in the case of ZW2SiC also, it forms as a thermal barrier layer, an insulation layer. So it protects the layers underneath, oxide the material underneath from further damage by the heat of the oxygen torch. And so although it is porous, it is not continuous. So there is a layer of silicon SiO2 ZiO2 inside, where the carbon fiber is oxidized and passed away as far as CO. But SiO2 ZiO2 layer forms inside. Now, if SiO2 is exposed outside, it will form silicon oxide and it will vaporize. So if it is inside, it may not happen. And so basically together it gives some protection at high temperature. The duration of exposure actually is for about varies between up to 10-20 minutes. So basically it is a lot more time compared to the exposure duration of re-entry vehicles when it is exposed. So it sees temperature between 1500 to 2000 degrees centigrade. So these tests are basically done to simulate such conditions. So finally, I'd like to conclude by saying that we had initially looked at multi-phase refractory silicide-based implantic alloys, and it is possible to achieve desirable combination of high temperature strength and oxidation resistance with improved fracture toughness by alloying. And 20 volume% SiC is optimum for ZW2SiC composites to get the best combination of thermophysical and ablation property, but fracture tolerance is not good. And gel casting provides us a pressureless, gel casting followed by pressureless sintering gives us a technique where we can make large sizes and complex shapes. And strength, thermal fracture toughness, thermal properties, damage tolerance of CFSiC composites depend on orientation and architecture of carbon fibers. Tensile strength increases with temperature because fiber pullout also increases with temperature. And hybrid composites deserve attention for superior fracture toughness and damage tolerance compared to ZW2SiC. Of course, not compared to SF-CFSiC, but they have superior ablation resistance compared to CFSiC. So that's why these hybrid composites are now drawing a lot of attention, and a lot of work is going on worldwide. So my student is working in collaboration with DMRL scientists in this. So with this, I'd like to acknowledge the contributions of my students, starting from Arvind Srivastava, who was one of my first MTech students, one of my first PhD students, Sharma Paswan, Shri Professor Sanat Kumar Roy, Dr. Kaushik Chattopadhyay, so who was Shri Professor KK Rai. So Paswan is in CSIR NML, Kaushik is in BHU. Kasturi Sala actually now is a faculty in IIT ISM Dhanbad. So I forgot to change this. And Manam Malik is faculty in NIT Durgapur. Sabyasachi Roy is somewhere in Europe. And he was a BTech student, a dual degree student. Sunil Kashyap is a faculty in IIT Jammu. And my present students, Ramya Krishna, Vidushni and Adarsh Mishra, whose name I took. And my colleagues, senior colleagues who have retired, was a KK Rai, Sanat Roy. My present colleague was Santanu Dhara at IIT Kharagpur, Dr. Uday Kumar at CSIR NAL, and retired scientist Dr. V. Panu Prasad, who was my colleague at DMRL. Presently, Dr. Manish Patel is there, and Dr. G. Balchandan, who has also moved out from DMRL, but he helped by making the silicide composites. And Professor Kamune Chattopadhyay and Professor Satyam Suhas helped us with some of the facilities at IISc, which we have used for the silicide work. And I also am thankful to the support of IIT Kharagpur, Central Research Facility, DML Hyderabad, CSI NAL, and ISC Bangalore. And the major funding came from the DRDO. So at least 3-4 projects, several projects we have obtained from DRDO since I joined here. And the latest one was a large project for develop gel cast alloys, which ended recently. And so this is the pictures of my research group in front of the IIT old building, and this is some Teachers' Day celebration or birthday celebration, and this is we are having dinners, and these are with my some past students, Kaushik, Manav, and Prasenjit. So when there was a conference in Hyderabad. So with this, I would like to thank you all, and I'll be happy to answer any question.
Thank you, Professor Mitra, for your excellent lecture on actually this design and development of materials for ultra high temperature aerospace applications. And here I may mention that Professor Mitra became actually INSA fellow few days back, and I requested him that whether actually he would like to give a lecture, and he readily agreed. We are really very, very thankful to him, and whatever, and I'm also happy to say so that 3 more actually lectures are on the pipeline, and it will be done in next few days. And they were all
actually there is some problem
recently INSA elected fellows. Okay. So now actually we'll have some question and answer. May I first request Professor Sanat Kumar that if you have got some questions, always you have, and this time also you will have. Sanat Kumar ji.
Yes, sir. Actually, I'm not really qualified for asking questions on this, although I like metallurgy as such. But I was curious to know something. You are making this by powder metallurgy project, isn't it? So now you showed a turbine blade, which I suppose is made by the same process.
Yeah, investment casting and direction certification. Yeah.
Investment casting, and it is not a metal, no, it is only powder metallurgy. It is right, or that means you make a powder, actually, you compact it, put it in a binder, and then heat it, and it becomes solid. I was wanting to, my question was like this: how does that blade compare if you had made it with a wrought material? For example, alloy steel or alloy itself. Of course, forget about the temperature, but otherwise, this will be much weaker than a wrought metal product, is it not? Why I am asking this is that in a turbine blade, particularly at the root, there will be a lot of tensile force. So I was wanting to know how this powder metallurgical process will withstand those forces, particularly in a jet engine when you're running at a very high speeds.
Powder metallurgy is not the correct process to make turbine blade. Turbine blade is made by
Okay.
directional solidification or investment casting.
Okay.
No,
Okay.
so that is the way, and we go for single crystal blade or directional solidified blade to reduce grain boundary area. Powder metallurgy can be used for making other components of blades. I mean, other components of jet engines, not turbine blade.
Okay. Then the next question is, you are making 100 millimeter by 100 millimeter tiles, isn't it?
Right,
That is,
right.
that is your
Ceramic
final
tile.
product. Sorry.
Yeah.
Yeah. So now that ceramic tile, how do you fix it to a, for example, in a rocket? It is for ablation purposes, you fix it. No, there has to be some kind of a adhesive with which you fix it, or that itself is the rocket material.
It has to be braced to niobium alloy. So that is another project, how to join it. So people have also used certain additives to join it to niobium alloy using lithium alumina garnet. And it can be then used. So actually we have developed a process where bigger ceramic tiles can be also made using this. We have made up to 100 by 100 mm, but even bigger can be made because we are an academic institute, we have limited facility.
Okay.
But in an
Understood.
industrial scale, it can be scaled up.
Okay. I
A
will
little
just
bit more optimization.
Yeah, I will just tell you the reason why I asked that question, which may be wrong also. Anyway, I was remembering that the shuttle, which was re-entering, the tile broke off. And
Right.
so that is what is making me worry about this, how this tile will get fixed and it will be standing correctly until it comes to the earth back again. That was
Right. Yeah. So for that only we have made it actually. So this is, so we have developed a process where these tiles can be made. Other even nose cones can be made because both leading edges and nose cones can be made. Different shapes can be made in the industry or by the DRDO. So we have given them the technology, and so it is up to them whether they want to use it. But now also, they are using CFSIC anyways, carbon fiber silicon carbide composite. So there is an effort to improve its property further by inserting ZRB2SiC. So
Okay.
ZRB2SiC they have done as an experimental basis. So in US also it has been developed. So there can be applications in future, but it is something which they have to decide where they want to use it and how they want to use it.
Okay, yours is in a laboratory scale. They have to make it bigger in the industrial scale.
We have
Okay.
done. We have taken a project, and we are basically a student has worked for his or her PhD. So it's basically we are interested in the academic part and
Yeah, okay,
developing the
understood.
product for them. Yeah.
Okay, you can't
Final thing they have to do.
you can't forge it or bend it or something like that. It has to be
Forging, we can make any shape by gel casting, and it will
Okay.
retain. It will also retain its shape, and it also will have sufficient handling strength. That is important because many of the green products they don't have handling strength,
Yes.
but this will have handling strength.
Okay, thank you, sir. I understood. Thank you, sir.
Dr. Sanjay, would you like to ask some question? You are mute. Anybody else would like to ask some questions?
Yes, sir, please. Myself, Suresh Panna, actually.
Yes, please.
Sir.
Suresh,
Sir, actually, it's a very insightful talk, but I have many things to understand actually, but only a couple of questions I'd like to ask, sir. One is that you told that this in the particulars that this carbon fiber silicon carbide composites, there is strengthening or increase in strength with temperature, sir, increasing temperature.
Right.
So due to that debonding, so is it for only this or a few other or many other also materials, or is specific to this particular material, sir?
See, carbon as such is strength. If you take graphite, its strength
Yes,
increases with increase in temperature. At high
Increasing,
temperature, strength is higher. So basically, there is an orientation preferred orientation of basal planes of carbon along
Yes.
the tensile axis. And that's why
Sure.
the strength increases, fibers. That is
Oh,
the fiber strength increases. And we also see more debonding. The interfacial residual stress decreases. So that
Sure.
all three contribute to the increase in strength that we observe.
So it's mainly specific to the carbon fiber.
Right,
sir.
right. Yeah.
Okay, sir. So another thing that and then pressureless sintering it means the density actually is quite high, sir, 98%. So
Right.
there also, sir,
We got
but
even
is it?
higher. We got close to 100% for
Yes,
certain
sir, yes, sir.
compositions.
Yes, sir. That is for specifically for some compositions, sir. So means what is the main mechanism there? Because normally pressureless sintering you don't get very high densities in common materials. Typically reach very high, you reach very high densities. So the densification is quite high during the sintering. Sir.
And then I went to a conference in US and there someone suggested to me, you hold at intermediate temperature to reduce the oxide impurities and then you'll get better density. And we tried it, it worked. So, yeah.
Okay, sir. Thank you very much.
Any other question? I have got actually few just
Yes, sir.
simple queries. Just for my knowledge check, I am not actually, as you know, not actually metallurgist or material scientist. So I would like to know that what type of material is being used today for supersonic jets for their body as well as actually nose.
Yeah, supersonic jets, I think body must be of aluminum alloy and titanium alloys.
Okay. And so far as nose is concerned?
I'm not sure exactly, but maybe some titanium alloy I can think
Okay.
of.
And the same thing is actually what type of things are used for the missiles and rockets.
Yeah.
Which are going for this space travel.
Yeah, they have carbon fiber, carbon composite. And basically the tip is made of carbon fiber, silicon carbide.
Okay, okay.
Yeah.
Okay. Now one more thing that I would like a little bit of your consent on this, that this entire lecture is actually recorded.
Okay.
If you do not have any objection, can we really calculate it? If you have got some objection, no.
No, I have no problem. I mean,
No,
I don't have
no problem.
No problem.
We can circulate.
Yes, you can circulate.
Okay. Now,
I mean, I'll be happy
Sanat
to
Kumar
answer
ji,
queries later.
please.
Yeah. I'm not able to hear
Sir,
you.
you are mute.
Okay, yeah.
Can you hear me now?
Yes.
Yes, yes. Please.
So, sorry for the late question, but anyway, how about the corrosion resistance of this material? Supposing a rocket falls into the sea or water, particularly I'm talking about water or steam, how does it work? Does it corrode? Does it make cracks? Is it porous? What happens to it? Corrosion resistance.
Yeah, so silicon carbide is very much corrosion resistant. It is used for seals in Navy for naval ships. So silicon carbide, if it is applied, silicon carbide coating is there. It will resist any kind of damage by seawater. So that is good.
Okay, sir.
Yeah.
Thank you.
Okay. May I now request Professor Renu Sharma to please propose a vote of thanks.
Good evening, sir. Namaste. Am I audible, sir?
Yes.
Yes, yes.
Thank you, sir. It's indeed my privilege to propose the vote of thanks on the behalf of organizing committee for today's 66th lecture in the distinguished lecture series. At the outset, I extend our heartfelt gratitude to Professor Rahul Mitra, sir. He's from IIT Kharagpur. for delivering a highly insightful and intellectual enriching talk on design and development of material for ultra high temperature aerospace application. Sir, your lecture beautifully highlighted the cutting edge research, challenges, and innovation shaping the future of advanced materials for aerospace technologies. We are truly inspired, sir, by your depth of knowledge and passion for research. Our sincere thanks to INA Bhubaneswar chapter, Shiksha Anusandhan deemed to be university, CSIR MMT Bhubaneswar, IIT Bhubaneswar, Nizer Bhubaneswar, as well as IEEE Bhubaneswar section for jointly organizing this distinguished lecture event. A special note of appreciation to all the distinguished fellows, faculty members, research scholars and students who have joined us this evening and made this session a meaningful with their enthusiastic participation. Finally, I express my gratitude to once again to the speaker for giving us such a wonderful lecture. Thank you, sir. Thank you so much. Jai Hind.
Thank you.
Thank you, sir. Okay, it was my pleasure to be here today and
No,
very
no, no.
nice to see all of
Absolutely. It
you.
was